some of the technologies that we need here. The video head-end device takes the audio and video received from the TV station and converts it into a format that can be streamed. So coming back to our diagram, TV station generates the content, delivers it to the video head-end. It may be via any type of network. And then this video head-end converts the video into, say, MPEG-4, use particular codecs, and then the video head-end uses protocols to send that video in packets across the IP network here. Commonly RTP is used, but there are other protocols as well. So the role of the video head-end is to generate the IP packets that contain the video and audio for the TV. At the receiving endpoint, we normally have a set-top box that can receive the content. That is in the home network. Some special device that can receive this stream of video and display it and convert it and display it on the TV. It may be built into the TV, it may be a separate device. What else do we need? All right. Some of the protocols commonly used, the ones we talked about with voice, can also be used for video delivery. RTP, the real-time transport protocol, can be used to deliver both audio and video, voice or TV. It's a generic protocol that carries any type of content. It just sends the packets. RTSP for controlling. So same as voice can be used there. The other things we need, especially inside the core network, is to be efficient, multicast, and sometimes quality of service control. The problem would be if we're watching TV, but some other users on other access networks are downloading files, making voice calls, then all of the content are just IP packets on this network. IP packets for voice, IP packets for video, IP packets for accessing websites. Without quality of service control, all those IP packets get the same treatment. If coming to this router, there's traffic from many different customers using the 3 different services arriving in this router, and this router starts to get overflowed. That is, this output link reaches its capacity. Then what's going to happen is that packets are going to eventually be dropped here. And if the video packets start to be dropped, then the receiver is going to get lower quality video. That's a problem, because if we want to deliver the same quality as we get over the normal TV network, we shouldn't allow too many packets to be dropped. So that's where we need quality of service inside here to give priority to different applications. Higher priority to video and voice, lower priority to web traffic, for example. Maybe higher priority to the customer that pays more, lower priority to the customer on the cheap plan. So inside the ISP core network, quality of service control is commonly needed. Without it, the quality would not be sufficient. So quality of service. Also, multicast is useful inside the core network. We have many subscribers on different access networks. So the ISP has access networks across the country and many subscribers. If they're all watching the same TV channel, then we should be able to use multicast. That is, from the video head end here, use multicast and just stream one copy of the packets representing that TV. One copy across the network, and where necessary, the routers split out, send a copy to these subscribers, send one copy to these, and one copy here. So that's the basics of multicast. Source sends one copy of the data. The multicast routers along the path make copies and such that it will reach all the subscribers who are watching that TV channel. Without multicast, if we have 1,000 people on this network watching the same TV channel, here we'd need to send 1,000 copies of those packets representing that same content, or carrying the same content. With multicast, we just send one copy here. And at the routers, normally at the edge, they make copies to send to the individual users. So multicast is very important if we want to stream video. We'll see some plots shortly that show the benefits. Other parts that we won't talk about much but are needed are things to authenticate users, make sure that you're a paying customer, that you're authorized to access particular content, and that can count how much content you're accessing so they can charge you at the end of the month. So all things about managing authentication and accounting is needed inside the network. We've spoken about multicast, how it works, and quality of service control. We've mentioned RTP and RTSP in previous slides. And what about the network technologies? Inside the core network and the access networks, what's needed? Well, we've spoken about these technologies as well. In the core networks, often optical fibre. SDH is common. PDH in the older networks, SDH in the current networks. Everyone's filled in their name, the piece of paper. Thank you. Only 1, 2, 3, 4, 5 people missing. There's 2. In the core network, often optical fibre is used nowadays, because we'll see shortly that we need a lot of capacity to deliver this TV. We'll do some basic calculations. Inside the access networks, basically from the home to the core network, different options, ADSL, especially the newer versions, optical fibre, coaxial cable, Ethernet, some different options there. Inside your home, normally Ethernet or wireless LAN. Let's look at some very simple examples of how much capacity do we need in these networks to carry the TV. Here's an example of a home where you have multiple people living in the home and wanting to use the services at the same time. A voice call, high quality voice call, requires about 64 kilobits per second. Without the normal requirement for a voice call is 64 kilobits per second. That comes from our voice has a frequency, we're normally up to about 4 kilohertz that we'd send across a voice call, and using Nyquist we sample at twice that rate, 8,000 samples per second, 8 bits per sample, one voice call, 64 kilobits per second. That's very small. That is, for this home, for someone to make a voice call, the network from the home to the public switch telephone network needs to have a capacity of 64 kilobits per second. That's easy. If you make, maybe there's multiple people talking at the same time, 3 different phones, then it's 3 times this. Let's say we want to give the users high-speed internet access. This is a bit old. High speed, several megabits per second is usually needed. 2 to 4, faster would be better. Tens of megabits per second would be better. But let's say each user in the home to their laptop, to their PC, to their mobile phone should be able to get around 2 to 4 megabits per second. If we want to watch standard definition TV, digital TV, we typically need about the same, about 2 to 4 megabits per second per channel. Standard definition TV, the resolution, the quality is on the order of DVD quality. 2 to 4 megabits per second includes the compression. That is, we have the video content, apply compression. We need to be able to stream at a rate of, say, up to 4 megabits per second to get reasonable quality. If we want high definition TV, we need faster streaming, up to 10 megabits per second per channel, per TV channel, per video stream that we want to watch. So this house, if there's multiple people watching TV and making voice calls and accessing the internet at the same time, we're talking about the house needing or utilizing, say, 15 to 30 megabits per second. Let's say the upper limit, 30 megabits per second. If you want to watch, maybe you have 2 TVs in the home and 2 people want to watch different channels at the same time, then if we want high definition TV, and if each channel was 10 megabits per second, then there's 20 megabits per second required just for the TV. Plus some for internet access. Someone else is accessing the internet at the same time, like web browsing. So now the question is, in our network, inside the home, inside the access network, and inside the core network, what technologies do we need that will support 30 megabits per second? Well, the bottleneck, that is, of those 3 networks, which one is it hardest to provide this 30 megabits per second is normally the access network. Think about in your home. If you're using Ethernet in your home, you've got 100 megabits per second. That's fine. And in a new network, 1 gigabit per second. So 30 megabits per second in your home is not a problem. With wireless N, wireless LAN N, what's the typical data rate with wireless LAN N? Not 1 gigabit. Wireless N, usually they say the maximum speed's around 300 megabits per second. But take into account overheads, still possibly more than 100 megabits per second. So delivering 30 megabits per second inside the home is usually not a problem. In the core network, if we're using optical fiber, then we're talking about gigabits per second inside the core network. Several gigabits per second from source to, from across the core network. Access network, that's usually where the problem will arise. That is, the technologies available today may not support 30 megabits per second. We'll come and look at some of them, those technologies. That part of the network is sometimes referred to as the last mile. That is, it's from the network provider's network, this is the last portion of the network to reach the customer, the last mile of the network. This is just an example of what capacity is required in the core network to support TV delivery. So let's look at the core network, this part. If we're using optical fiber, what do we need as a capacity to support TV delivery? Using the numbers that we had before, focusing, let's say, on HD TV, it depends upon the number of channels we want to be able to stream at the same time. Because we have multiple users on different access networks, and all of our content comes from this video headend and is streamed across the core network. If this user is watching one channel and this is watching another channel and another channel, from the perspective of the core network, there must be 3 different video streams in parallel. One for the content for channel 3, one for the content for channel 5, and one for channel 7. So the capacity needed in the core network depends upon the number of channels we want to be able to support, that is, deliver and offer to the customers. So we see on this axis the number of channels, and if each channel requires, say, in this example, the assumption I think is a HD TV channel requires about 16 megabits per second, approximately. One channel of HDTV in this plot requires 16 megabits per second. So simply, it's a linear increase. As we increase the number of channels that we want to offer to the customers, the capacity required in the network increases. Following the blue line, if we have 10 channels on offer, then our core network needs to support around 140 megabits per second. If we have 100 channels on offer, we need to support about 1.6 gigabits per second. That's the core network. So the more channels, the more capacity needed in the core network. Supporting 1.6 gigabits per second in the core network with optical fibre is possible nowadays, not a problem. That's for normal TV delivery. The more channels we want to offer, the more capacity we need in the core network. It's independent of the number of users. Because if we use multicast, for most part of the core network, even if we have 1,000 users watching channel 3, using multicast, we're just sending one stream across the core network. It's only at the endpoints that we start to make copies of that stream. So independent of the number of users here. If you have 100,000 subscribers, still, this is the capacity you needed to support that TV. But the problem arises if you want to support not just normal TV, but video on demand. How does that work? Who has video on demand? Not many people. How does it work? Yeah, YouTube, that's our other approach of web-based file delivery. TiVo, but how does it work from the user's perspective? How would you like it to work? You visit some page on your TV, you select a movie and you press play. And that movie starts playing instantly. That's the idea of video on demand. A movie, some sport event, whatever. That is, with normal TV, you watch whatever is programmed to be sent. That is, the program is set by the TV TV station. With video on demand, you choose the content to watch at that particular time. If we want to support video on demand, we must use unicast. Because with video on demand, the chance that two people are watching the same video or demand the same video at the same time is very low. So we cannot use multicast. This user wants to, let's say, at 8 p.m, they want to watch some movie, video 1, and then 10 minutes later, some other user here on the same network at 8:10, they go and check and choose a movie to watch, and they choose the same video, the same movie, video 1. If we want to allow the users to start the video whenever they choose, then we must use unicast. That is, we stream a copy of that movie from here across the core network to this user, and then 10 minutes later we stream a copy of the same movie to this second user. We cannot use multicast because we cannot send at the same time. That is, the first packet sent to user A is sent 10 minutes before the same packet needs to be sent to user B. So the problem with video on demand, we need unicast. And with unicast, the capacity we need now depends upon the number of subscribers. Because if we want to allow 100,000 subscribers, we've got 100,000 customers, so this is a large network, a large operator. If we have 100,000 customers and we want to allow them to do video on demand, that means potentially 100,000 videos are started and are running on our network. then the capacity we need is 100,000 times by our 16 megabits per second. We're up to 25 gigabits per second. That's the capacity needed in the core network. That is starting to stretch the current capacity of networks. Most core networks in the order of 1 or 2.5, maybe 10 gigabits per second. 25, 30 gigabits per second is going to be very costly for the core network. So that is a problem. If we want video on demand, we need unicast, but that greatly increases the capacity if we want to allow all customers to do video on demand. How can we get around that? I want to support video on demand, but we want to use multicast. Can we improve? What about our two users? User 1 chose at 8 p.m. to watch video 1. 10 minutes later, user 2 chose the same video. Okay, we could do some caching. So we send the video to this user, and in a server closer, that is maybe here, if the video went through this router, we could cache a copy so that we could later stream it to here. So that would be one approach, that we, instead of having to stream from the video head end across the entire core network, we can stream it from a 10 minutes later, start streaming the same video from a closer location. So there's one approach. Still needs to be sent partially across the network though. Anything else we can do? Do not allow pure video on demand. Force the users to start watching at a particular time. Everyone, so you can either start watching a video at 8 p.m. or at 8:30. You cannot watch it immediately. So there's some scheduling such that let's say another user started, in our case, at 8:15, the same video. With video on demand, we'd need normally 3 streams with unicast. 3 different users starting at 3 different times. As an alternative, we can force the users, okay, they want to watch it at 8:10, it will not start until 8:30. This one will start at 8 p.m, this one will start at 8:30, and this one will start also at 8:30. Now, at least these 2 users, we can use multicast because the stream needs to start at the same time. So that's a way to get around this need for pure unicast by forcing the users not to be able to select the exact time, but to follow some schedule, so that it's likely that we can still partially use multicast for some of the users. Maybe some of the users we need unicast, but if many people want to watch the same video around the same time, we can use multicast. So that's a practical way. But video on demand creates a problem. It normally depends upon the number of subscribers that we want to allow to access video on demand. So that's about the core network. So we're talking about gigabits per second needed in the core network. That's capable with optical fibre, SDH, we can support those technologies. Inside the home, we're okay if we need to support 30 megabits per second per user. Our current technologies will support that. What about the access network? Some options we have. So the access network is, say, from your home to the ISP's core network. We've mentioned some different options. We've got ADSL and ADSL2 and ADSL2+. We know ADSL uses copper telephone lines. That's an advantage. We use the existing network infrastructure. Some typical speeds that we can achieve with both ADSL and ADSL2+. Note that it depends upon distance you are from the exchange. the way that ADSL works is, as a reminder, we have our home, our telephone line to some telephone exchange, a local exchange, and normally that exchange, the ISP has a router inside the exchange, and that connects to their core network. So from the home to the exchange is what we're talking about as the access network. Then we can go to optical fibre in the core network. With ADSL, the data rate that we can support from the home to the exchange is getting up to 20, 25 megabits per second. Only if we're very close to the exchange, 300 metres from the exchange. Who lives within 300 metres of a telephone exchange? It's hard to know. Some people would, some people would not. So if we want to use ADSL and we want to support IPTV, we're pushing the limits of what ADSL can support. Only some users will be able to get access to these speeds which are needed. As the users are 3-4 kilometres away, they may not get a high enough speed to support high definition TV streaming. So ADSL 2 is one option for the access network. To improve, the main options are usually to use optical fibre to the home or close to the home. The problem here, the core network uses optical fibre, high speed, but from the exchange to the home we use just the copper line. And with copper here, the longer the distance, the lower speed we can support. And copper can support only much lower speeds than optical fibre. So we'd like to remove this copper line, but that's expensive. So we'd at least like to reduce the distance. Bring the home closer to the exchange, not possible, you cannot move the home. Bring the exchange closer to the home. That's what we'll see we can do with the next options. Bring fibre, this part, optical fibre, closer to the home. That is, shorten the length of the copper that we use. That's the concept here. Let's look at 3 examples of that. Fibre to the node, fibre to the curb, and fibre to the home. We have our, why are these red? We have our home with ADSL. Here's our telephone exchange. And then it connects onto the core network using optical fibre. And use the copper. That's the example using ADSL. Copper to the exchange and then optical fibre. Fibre to the home, deliver optical fibre into the home. That's the best case scenario. Here's our core network of our internet service provider. With ADSL, we connect that core to an exchange and then use the copper. Fibre to the home, we have a router, and then we use optical fibre direct into the home. So that's the best case because optical fibre is much faster than using copper. We can get high speeds, and we get those high speeds all the way into the home. The problem with this is it's expensive. For every home that you want to deliver the service to, you need to dig the holes and put the cables in. And that's very expensive in large cities. So one option, but an expensive option. The best option in terms of speed. So let's look at some alternatives midway between these two. And that's what we get with fibre to the curb and fibre to the node. The approach is to bring this exchange closer to the home. Still use the copper line from the home to this exchange. In fact, it won't be a telephone exchange, it will be a special device that interconnects to our fibre network, but to reduce the length of our copper link. As we saw with ADSL, the shorter the length of the copper link, the higher the speed. So, what have we got? Fibre to the node. The concept is that we have some special device, say in some neighbourhood, in some suburb. Maybe we have one exchange for a large area of the city, and let's say that exchange, we have 100,000 people connecting to that one exchange. The idea is to have multiple nodes that those users connect into. So the copper link now goes to this node. And maybe on the node we talk about hundreds, thousands of homes. That is 1,000 users in one area connect to this node, and we have another node to connect another 1,000 users. So we put these special devices across the city, and instead of connecting the copper wire into the exchange, intercept it at this node. And in fact, we could then go to the node to the exchange via copper, but then importantly, optical fibre. Either direct into the core network or into the exchange. Different options. The idea is to shorten this copper path. And with a shorter copper link, we can get higher data rates. And this is optical fibre. But the trade-off is that we still use some copper path. By introducing this new node into the network, we don't have to have optical fibre to all homes, so we save money in deploying the network, but we need to introduce these new nodes, so it's more expensive than just using the telephone exchange. So this is referred to as fibre to the node, where the node normally covers hundreds or thousands of users or homes. And another approach, same approach, is to bring this node closer to the user, to the curb. That is, let's say you have a street, there are tens of homes along that street, then you put some special device along that street, all of the homes connect into that special device, and then that uses optical fibre, the rest of the path. We've shortened the copper link and used the optical fibre for the rest of the way. That's the concept. This would be fibre to the curb. And there are other terminology. There's fibre to the premise, which is similar to fibre to the home, maybe a couple of others as well. The main concept, shorten the copper path, because that's the bottleneck in our performance. The shorter it is, the higher the speeds we can achieve. Use optical fibre as far as possible, but to make a trade-off with cost, we may not use optical fibre all the way to the home, but to some special devices to shorten that copper path. And different operators and different countries in the world have chosen different approaches depending upon their requirements. Any questions on... So these are common ways for access network to get IPTV delivered. Any questions?
Teacher, in the copper zone,
Yep.
which technology we use?
So then, okay, in the copper, the copper link to the node, whether it's fibre to the curb, fibre to the node, or even to the exchange, what technology do we use? Normally DSL, not necessarily ADSL. That is, on shorter distances, things like VDSL are sometimes used. So over very short distance, tens of metres, ADSL doesn't have to be used. So VDSL gives higher data rates, but only works over very short distances. But DSL normally across the copper links. Any other questions before we move on? Maybe it would have been easy to draw 4 separate diagrams, but I think you get the point that, okay, option 1, copper to the exchange, option 2 and 3 to these nodes, and the difference really is how many nodes per user do we have? How close is the node to the end user? Or optical fibre direct into the home? Other options? Ethernet, wireless LAN, but not so common. Mainly just for businesses. So it's a trade-off between speed and expense. Speed and cost. So for delivering IPTV, in summary, in the home network, we've got technologies like Ethernet and wireless LAN that can support the bandwidth required. In the access network, we've got options like ADSL, but perhaps more suitable are these fibre-based options. In the core network, optical fibre is primarily used. The issues are that we can use multicast for TV delivery inside the core network. For video on demand, we either need to do some variation of video on demand or we'd have to use unicast. And all of the content comes from some video headend that streams the content across the IP network. And our IP network, in practice, will normally carry TV content, voice content, and normal web or internet content. So we access 3 different networks via the one core network. That finishes our topic on multimedia. Any questions? We've only got one topic remaining this semester. Although there are 2 sets of lecture notes, it's the same topic. Any questions on multimedia? If we can get started on the next topic today, we'll hopefully finish Wednesday next week. So our last topic for this course is peer-to-peer systems. We'll go through the very basics or some concepts of what is a peer-to-peer system and some different approaches for discovery in peer-to-peer systems. And then we'll look at some example technologies. One of them, although it's in a different set of slides, we'll mix it in here, is looking at BitTorrent and peer-to-peer file sharing. But today we'll just introduce some concepts. We'll try and describe what we mean when we say peer-to-peer or P2P. And we'll talk about one important problem or challenge in peer-to-peer systems, how to locate resources. The next set of slides, we'll then move to the next set of slides, which is more about how do we transfer content or resources in a peer-to-peer system. And then we'll finish by comparing some different approaches. Peer-to-peer systems, or peer-to-peer, the phrase covers many different things and is used to refer to many different things. It can refer to applications, protocols, concepts, algorithms. It can be used in many different cases. It can be used in a file system, a distributed file system, caching, online gaming, special distributed or grid computing. We'll use file sharing as an example, probably because most of you are maybe familiar with that. But peer-to-peer and the technologies we talk about can support many different applications. We won't cover too much on here. What's the motivation of peer-to-peer systems? The basics is that a centralized system, when we have many users and many resources, we can have a bottleneck in terms of using a centralized system. Consider the basics of a centralized system versus a distributed system. A centralized system, there's one central device, server, that all the content goes via, or all the users access their content via. In a distributed system, the resources are distributed amongst all the users. The problem with a centralized system is that that central server can be a bottleneck. If it fails, the whole network fails, the whole system fails. That's a common advantage or trade-off between centralized and distributed. So there are some benefits of distributed systems, and a peer-to-peer system is an example of a distributed system. You can read through those examples. I think you've seen or understand the difference. And similar here, a client server, which is a centralized system, is asymmetric and centralized. We have a client accesses a server, and normally many clients access the same server. That server becomes a bottleneck. If the server fails, the clients cannot access anything. If the server becomes slow, the service to the clients becomes slow. So that's the disadvantages of a client-server system. A distributed system, a peer-to-peer system, which we'll talk about, is symmetric in that the peers talk direct with each other and the exchanges are the same in both directions. And it's decentralized. There's not one central server that we rely on. The advantages being the opposite of that with a client-server system. Yeah?
What does it mean by symmetric and asymmetric?
Okay, client-server system. Here's our server. Here are some clients. Normally we have multiple clients. And a peer-to-peer system the users, whatever the system is providing, whether it's providing file access, whether it's providing access to shared resources at the server or a search index, in a client-server system, the users are the clients. They want to get access to some service. The server offers that service. It's asymmetric in terms of we have differences between the types of users or the types of devices. The clients, here we have 4, all accessing a single server. In a peer-to-peer system, here are our users. I'll call them P for peers. They access services directly from others, and if we look at the number of links coming into each device, conceptually, the server has multiple clients accessing it. The client only has one communication to the server. So there's the asymmetry in terms of the set of communications. Many clients access the server, only one server accesses the client. In a peer-to-peer system, we have symmetry in terms of this peer may communicate with 3 other peers, this peer may communicate with 3 other peers, and each with 3 other peers. So there's symmetry in the number of connections there. So this is an example of a centralized system. A client server is a centralized system. A peer-to-peer system is a distributed system. Same with a centralized versus distributed database. Any centralized versus distributed system, the same arguments apply with the trade-offs. Centralized, we have a single point of failure. We have bottlenecks at the server. If the server is slow, the clients can't access the service. In a peer-to-peer system, those problems are not present. The advantage of a centralized system is it's easy to control access to resources and functionality. For a client to access some resource, they must go through the server. Therefore, we can have security controls over, do you have permission to access that resource? The server can control that. So long as the server knows who is allowed to access which resources, the server can control which clients can access resources. In a peer-to-peer system, which node controls who accesses what? There's no centralized point of control. So in a peer-to-peer system, it's hard to control access and in turn provide security to resources. Another thing, in client-server systems, the algorithms we need to support some service are usually simple and efficient. Imagine searching for something. In a client-server system, if a client wants to search for something, the server can store an index of all the resources. To search for something, send a query to the server sends back a response. In a peer-to-peer system, if peer 1 wants to search for some resource, who does it ask? It has to ask all 3 peers where that resource is. In general, the algorithms needed in peer-to-peer systems are much more complex than in centralized systems. So we should, because we're only talking at a very high level at the moment. We haven't got to the details. Go. BitTorrent, we'll talk about some different example applications. One is BitTorrent, and we'll explain it has characteristics of both a client-server system and a peer-to-peer system. It depends upon what we're talking about, whether we're talking about how do we find resources or how do we transfer resources between devices. Here we're just talking about the general concepts. But what does a peer-to-peer system do? If you think about peer-to-peer file sharing, there are 2 main things. How do you find a resource? And then how do you transfer that resource to your computer? Okay, so peer-to-peer file sharing is about the resources being files, and people want to access those resources. Two problems. How do you efficiently transfer those resources, and how do you find them in the first place? We'll see BitTorrent uses a peer-to-peer approach for the transfer of files. In some parts, or at least in older versions, it used a client-server approach for how to search for files. So it's not so simple that one particular application uses just one of these approaches. In practice, we'll see a combination. Let's go into some details so this becomes a bit clearer. Just some terminology. Peer-to-peer systems can refer to applications, protocols, and algorithms. So again, when we say, is BitTorrent a peer-to-peer system? Well, again, we need to be careful. What are we talking about? The protocol for BitTorrent, an application, the algorithms that it uses. There are some differences. And there are different ways to classify peer-to-peer systems, whether they're applications, platforms for developing applications, or algorithms. We're not going to go through and compare them. What we want to do is look at the problems that need to be solved for peer-to-peer systems. And we'll get a little bit more specific here. Consider there are thousands of computers in a network. Those computers have files that they're making available to other computers. So we have file sharing is the application. Then your computer wants to access and download a file. In a client-server system, what you would do is you would go to a well-known server and download that file from the server. That is, there's a web server that has a file. Your client accesses the server and downloads from the server. In a peer-to-peer system, we've got two issues. We've got the issue of how do we find the file? In a peer-to-peer system, we've got all of our computers in our network, maybe 1,000 computers. Files are spread amongst those computers. I'm searching for one file. How do I find that file? That is, how do I find the peer that has that file? That's the first problem. In a client-server system, normally a server would have an index of the files that it has available, and I can easily submit a query to the server. In a peer-to-peer system, finding a file, more generally locating a resource, is a problem that we need to address. The other thing, which we'll go through later, is, okay, I find that this file that I'm looking for is available on 10 different computers in our network, the same file. In a purely centralized system, I may download that file from one server. We'll see in some peer-to-peer systems an advantage can be had by downloading the file from multiple servers at the same time. That is, download a part from one server, another part from another server, and so on. To give some performance advantages in the download. We're going to first concentrate on how do we locate resources in a peer-to-peer system. When we look at the next set of slides and look at BitTorrent specifically, we'll look at how can we efficiently transfer a file, the resource, from some servers to a client. First, how do we locate resources? We have this problem. There are a group of peers, a group of computers in our network. That group of peers we refer to as G. Each peer has an address. Maybe it's an IP address, or an IP address and a port number. But in general, each peer has an address in that group, peer P or address P. And a peer may store a set of resources. We will use in the examples files as resources, but the resource could be something else. Could be storage resource, it could be computational resource. Each peer has some resource that it's willing to make available to other peers. So peer P has a set of resources R of P. And we can identify uniquely resources by some key, some ID. That's what we assume at the start, some key K. If we have a key for some resource, then we need to find the peer that stores that resource. To do this, we need some index that maps keys to peers. And what we'll look at in the next few slides is what are the different approaches for maintaining this index. Let's try and illustrate that with a very simple example. We have a set of peers in our system, 4 peers. Call this one has the address P1, P2, P3 and P4. Each of these peers, these computers, have some resources that they have available. Let's call this resource 1 and resource 2. Peer 2 has resource 2 and resource 5 available. Peer 4 has no resources. Peer 1 has resource 3, resource 4 and resource 5. So that's our current system. We have 4 peers. They have some resources available. The idea is that one of the peers is looking for a resource. It needs to find the peer that has that resource. How to locate the resource. Just the notation we used here, R of P, that is, we could say the resource set of P3 equals R1 and R2. That is, the set of resources available from peer 3 is R1 and R2. Each resource has a key. So let's, as an example, imagine the resource is a file. The key is some identifier of that file. And in my case, I'll map directly, so resource R1 has key K1, R2, K2, and so on. If a resource is a file, what's a possible key? What could you use a key as a key for a file? Something that identifies that file. What would you use? Or what could you use? I want to look for a resource in the system. I want to look for a file. If I send a query, what would I include in that query? I'm looking for a file called ITS413.mp4. If I send a query and I want to look for that, what would I include in the query as a key that identifies that file? File name. Okay, there's one approach. The key could be the file name, a very simplistic approach. The resource is the actual file. The key is some identity for that file. A file name is one case. In large networks, a file name is not so good because we may have 2 different files. The bits inside those files are different, but the file name may be the same. So how do we differentiate? That is, you create a file, ITS413.mp4, someone else creates another file, gives it the same name, and then I go searching and send a query. I'm looking for ITS413.mp4. Which one is returned to me as a response? If we just use file names, often file names are not unique. In practice, we can take a hash of the file. Everyone remember hash functions? explain to us what a hash function does.
One-way encryption.
One-way encryption, okay, that's picks up a couple of points. One-way is important. Encryption, almost. Hash function, let's say some function h takes some input, some data, some sequence of bits, and returns as an output some, let's say, hash value, or simply lowercase h, where this function has the properties that in practice, if you take two different pieces of data as input, you'll get two different hash values as output. There's one property. That, and the same data as input, you'll get the same hash value as output. That the hash value is small and fixed in length. And a one-way property means that usually, given the data, you can find the hash value, but given the hash value, you cannot find the original data. But that's more for security purposes. But we don't necessarily need that in our system. The important thing, the hash of some file 1, gives us some hash value, h1. If we hash a different file, even if it has the same name, but a different sequence of bits, file 2, we'll get another hash value, a different hash value. The idea is that all files, all different files, have a unique hash value. In practice they do, in theory it's not always true. So we can use the hash value to uniquely identify a file in a system. What was the other property? The hash, and the hash value is usually small and fixed length. Whereas the data, the input, can be variable length. I have a file, maybe it's 10 megabytes in length, some video file. I apply a hash function on it, hash of that file, and I get some value, h1, which may be 128 bits. So the hash value is just a small value that in practice uniquely identifies that file. If I have another video file which is 20 megabytes and apply the same hash function, I'll get another hash value, also 128 bits. The same hash function will always produce the same length output, but the input may vary, the size of the input. Two example hash functions you may have heard of. MD5 is one, SHA is another. They are common hash functions. Sometimes when you download a file from a website, that website will also display the hash, maybe the MD5 hash of that file, with the idea after you download the file, you calculate the hash of the file, and your calculated value compared to the published value should be the same. If they're not the same, then the files are different. So how do we use the hash value in searching, or in our peer-to-peer system? If we know the hash of a file, when we send a query, if we can send that hash value in the query, then we distribute that query through the network, and the people who receive the query can check the hash value against the hash of the files that they have and see if it matches. The hash is an example of a key. So when I say K1, it could be the hash of resource R1. It could be, in a simpler case, the file name, but file names are generally not unique. Hash values are, in practice, unique. So now, what's our problem here? We have a peer, P4, that's looking for a resource. Assuming that peer has a key that they're looking for. Find resource, so the challenge is find resource with key K2. Peer 4 wants to find the resource with key K2. How do they find it? What does peer 4 do? What does peer 4 do in our network? Peer 4 wants to find a resource with key K2. We see the sets of resources stored by each of the peers. What does P4 do? What could it do? There's different things. What's it going to do? If you're peer 4, what are you going to attempt to do?
By K2.
You know key K2. That's, let's say it's a file name you're searching for. You want to find the resource. What are you going to do? Send query. Where are you going to send the query to? Broadcast, okay. One approach, P4, looking for resource identified by K2. Send a query to everyone in the network saying, I am looking for resource identified by K2. Broadcast it to everyone. P1, P2, P3 will receive that query. P1 will either not reply or give a negative response because P1 doesn't have resource 2. P2 will reply, P3 will reply. So there's one answer. And we'll see that that's one way to find a resource. Very inefficient. Let's now have 100,000 peers all across the world. If I want to find resource R2, send a message to 100,000 computers in the internet, then if everyone does that, then we'll overload the internet. That is, it's very inefficient. Another approach. So broadcast is one extreme approach. Another extreme, introduce a server into the network. On that server, publish or store an index that maps resources to peers. Where is resource 1 stored? Resource 1 is on peer 3. So the server would store some index. Resource 1 is on peer 3. Resource 2 is on peer 3 and peer 2. Resource 3, peer 1. And resource 5 is also on peer 2. Here's the other extreme. So the first approach, broadcast. That's one approach. Another approach, let's have some other device in the network. So I'll draw it over there, but out of space. So we now have 5 devices, 4 peers, and a server, where that server has an index. How did it get that index? If all the peers contacted the server and said, I have this set of resources. The server stores some database or this index, and now when peer 4 wants to find the resource identified by K2, they send a query to the server. The server looks up the index, looking for K2, that means resource 2. The server sends back a response saying, contact P2 or P3. There's the other extreme. What's this approach? It's our client-server system. Our peers are now clients, at least in searching. The approach, these 4 peers tell the server what resources they store. When they want to locate a resource, they simply send a query to that server, and the server looks up its index and sends back a response. So this solution using the server for resource location is a client-server solution. The first solution, broadcast, is a pure peer-to-peer solution. There was no server involved. What we'll look at tomorrow morning is some solutions in between that combine them, that are a mix between client-server and the full broadcast approach. Let's look at them tomorrow.